Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the enthalpies of formation and combustion. In this text, we do not intend to deal with nuclear energy. We have mentioned in Project 2 that the molecules of a system possesses energy in various forms such as sensible and latent energy, chemical energy, and nuclear energy, as illustrated in the figure. We also ignored chemical energy until now, since the systems considered in previous projects involved no changes in their chemical structure and thus no changes in chemical energy. Consequently, all we needed to deal with were the sensible and latent energies. During a chemical reaction, some chemical bonds that bind the atoms in two molecules are broken, and new ones are formed. The chemical energy associated with these bonds in general is different for the reactants and the products. Therefore, a process that involves chemical reactions involves changes in chemical energies, which must be accounted for in an energy balance. Assuming the atoms of each reactant remain intact and disregarding any changes in kinetic and potential energies, the energy change of a system during a chemical reaction is due to a change in state and a change in chemical composition. That is, therefore, when the products formed during a chemical reaction exit the reaction chamber at the init state of the reactants, we have delta E state equals 0, and the energy change of the system in this case is due to the changes in its chemical composition only. Consider the formation of carbon dioxide from its elements carbon and oxygen during a steady flue combustion process. Both the carbon and the oxygen enter the combustion chamber at 25 degrees centigrade and 180 am. The carbon dioxide formed during this process also leaves the combustion chamber at 25 degrees centigrade and 180 am. The combustion of carbon is an exothermic reaction. Therefore, some heat is transferred from the combustion chamber to the surroundings during this process, which is 393,520 kilojoule per kilomole carbon dioxide formed. The process described above involves no work interactions. Therefore, from the steady flue energy balance relation, the heat transfer during this process must be equal to the difference between the enthalpy of the products and the enthalpy of the reactants. That is, since both the reactants and the products are at the same state, the enthalpy change during this process is solely due to the changes in the chemical composition of the system. This enthalpy change is different for different reactants, and it's very desirable to have a property to represent the changes in chemical energy during a reaction. This property is the enthalpy of reaction, HR, which is defined as the difference between the enthalpy of the products at a specified state and the enthalpy of the reactants at the same state for a complete reaction. For combustion process, the enthalpy of reaction is usually referred to as the enthalpy of combustion, HC, which represents the amount of heat released during a steady flue combustion process when 1 kilomole of fuel is burned completely at a specified temperature and pressure. It is expressed as the enthalpy of combustion is minus 393,520 kilojoule per kilomole for carbon and the standard reference state. The enthalpy of combustion of a particular fuel is different at different temperatures and pressures. The enthalpy of combustion is obviously a very useful property for analyzing the combustion process of fuels. However, there are so many different fuels and fuel mixtures that it is not practical to list HC values for all possible cases. Besides, the enthalpy of combustion is not of much use when the combustion is incomplete. Therefore, a more practical approach would be to have a more fundamental property to represent the chemical energy of an element or a component and some reference state. This property is the enthalpy of formation, HF, which can be viewed as the enthalpy of a substance at a specified state due to its chemical composition. To establish a starting point, we assign the enthalpy of formation of all stable elements a value of 0 at the standard reference state of 25 degrees centigrade and 1 atm. Perhaps we should classify what we mean by stable. The stable form of an element is simply the chemically stable form of that element at 25 degrees centigrade and 1 atm. Nitrogen, for example, exists in diatomic form and 25 degrees centigrade and 1 atm. Therefore, the stable form of nitrogen and the standard reference state is diatomic nitrogen N2, not monatomic nitrogen N. If an element exists in more than one stable form and 25 degrees centigrade and 1 atm, one of the forms should be specified and the stable form. For carbon, for example, the stable form is assumed to be graphite, not diamond. Now, reconsider the formation of carbon dioxide from its elements C and O2 and 25 degrees centigrade and 1 atm during a steady flow process. The enthalpy change during this process was determined to be minus 393,520 kilojoule per kilomole. However, each react is zero since both reactants are elements and the standard reference state and the products consist of 1 kilomole of CO2 and the same state. Therefore, the enthalpy of formation of CO2 and the standard reference state is minus 393,520 kilojoule per kilomole. Another term commonly used in conjunction with the combustion of fuels is the heating value of the fuel, which is defined as the amount of heat released when a fuel is burned completely in a steady flow process and the products are returned to the state of the reactants. In other words, the heating value of a fuel is equal to the absolute value of the enthalpy of combustion of the fuel. The heating value is called the higher heating value when the H2O in the products is in the liquid form, and it is called the lower heating value when the H2O in the products is in the vapor form. The two heating values are related by where m is the mass of H2O in the products per unit mass of fuel, and HFG is the enthalpy of vaporization of water at the specified temperature. Higher and lower heating values of common fuels are given in Appendix Table A17. The higher heating value of a fuel is equal to the sum of the lower heating value of the fuel and the latent heat of vaporization of the H2O in the products. When the exact composition of the fuel is known, the enthalpy of combustion of that fuel can be determined using enthalpy of formation data as shown above. However, for fuels that exhibit considerable variation in composition depending on the source, such as coal, natural gas, and fuel oil. It is more practical to determine their enthalpy of combustion experimentally by burning them directly in a bump calorimeter and constant volume, or in a steady flow device. Okay, that's all for this task. Thank you very much, and see you next time.